We have seen earlier that a resource allocation graph can be used for deadlock avoidance if there are single instances of resource types. But if there are multiple instances of the resource types, then Banker's algorithm can be used for deadlock avoidance. Also, avoidance algorithms, they require that each process must a priori claim the maximum number of resource instances it will be using. That means each process before beginning its execution has to declare and claim that this is the maximum number of resource instances it might use during the course of its execution. However, this number may not exceed the total number of resources which are available in the system. So whenever a user requests a set of resources, then the system must determine that if that resource is allocated, then will that leave the system in a safe state or not? After it has determined that, so if it knows that if the allocation of that resource will leave the system in a safe state, then the resources are allocated. Otherwise, the process has to wait till some other thread or process releases enough resources as required by the requesting process. There are certain data structures which are required for the Banker's algorithm. So we are assuming over here that n is the number of processes and m is the number of resource types. And in this example, we are taking that the number of processes are 3 and the number of resource types are 4. So the first data structure that is required is a vector of length m. So available is a vector of length m, and since m is 4 over here, that means this will have 4 elements. This is referring to the resources which are available in the system. So if we are having 4 resources types R0, R1, R2 and R3, then if this value is 5, this element is 5, that means 5 instances of R1 resource are available, 3 instances of resource R2 are available, and so on. So if available j is equal to k, that means k instances of resource type Rj are available. Next is the max data structure, which is an n by m matrix. N is 3 and m is 4. So this is a 3 by 4 matrix. That means there will be 3 rows and 4 columns. Each row is representing a particular process. So we have P0, P1 and P2, and it is having 4 columns. Each column is representing a particular resource type. So R0 to R3, because we are taking m is equal to 4 in this example. Now, if a particular element max ij is equal to k, suppose let's say this value over here is equal to k, then it means that process P1 can at most request 4 instances of resource R1. This we know, this information we have because each process has declared a priori how many maximum number of resources it might require. So max ij is equal to k represents that process Pi may request at most k instances of resource type Rj. The next data structure is the allocation matrix, which again is an n by m matrix similar to the max matrix. Max matrix was telling us how many maximum instances process Pi may require. Allocation matrix is telling us how many are currently allocated to process Pi. That means if Pi is allocated k resources currently, then allocation ij will be equal to k. Then we have the need matrix, which again is an n by m matrix. This shows that Pi may need k more instances of Rj to complete the task. Now, the maximum that any process that would require is max. Currently, it has been allocated allocation ij resources. So, need ij will be equal to the maximum that a process requires minus the currently allocated resources. So this is how the need matrix will be computed. Now we will see how the system will check whether the system is in a safe state or not. So what is the safety algorithm? So here we will have work and finish vectors which are of length m and n. So work is corresponding to the number of resources and finish is corresponding to the processes. So work we will initialize to be equal to available. We have seen that available is a vector of length m which shows how many resources are currently available in the system. So work is a vector which is equal to available and it is representing how many resources are currently available in the system. We will also have a vector finish which has either a value false or a value true for all the n processes in the system. If finish I is equal to false, that means the process has not finished. It is still wanting or waiting for it to be completed. It is still waiting to be executed. If finish I is equal to true, that means the process has completed its execution and does not require any more resources. So what we have to do is we have to find an I, the value of I, such that finish I is equal to false. That means we have to find a process which has still not yet completed and its need is less than the work. What is work representing? Work is representing the available resources. So what is that process which has not yet completed and its requirement, its need is less than what is available in the system? Because if we can find such a process which is waiting for resources and its requirement is less than the available, then that means resources can be allocated to it. So we have to find that particular process, that particular value of I which is representing that process. If there is no such I, then we will go to step 4. Else what we will do is we will come here, we will allocate the resources to the process because its need was less than work, and we assume that the resources were allocated and now the process has executed. So if the process has executed, that means its finish will become true, and if it has finished its execution, it will release its resources. So whatever were the resources which were allocated to this particular process, they will be released. So they will be added to the work vector which is showing the available resources. So whatever allocation number was there for this particular process I, we will add that back to the available resources which is represented by work, and finish I will be equal to true, showing that that process has finished. And then we will go back to step 2 and find another I, that means another process which is yet to complete and its need is less than work. In the last step, we check if finish I is equal to true for all I. That means all the processes have been allocated resources and they have completed execution. That means the system is in a safe state. We have been able to find the safe sequence. And what is the safe sequence? You can check my earlier video on the deadlock avoidance, which discussed what is a safe sequence. So that means we have been able to find the safe state, and that means the resources can be allocated as per the requirement of the processes. Now let's see, if a particular process Pi requests for a particular resource, then how do we handle that request? So each process will put in some request for the resources, and we will have a request vector for a process Pi. So this request vector would also be of the size of m resources, because that is the number of resources that we are having in the system. So suppose if this is the vector, request vector of process. That means it now wants or is requesting for one instance of resource R0, two instances of resource R1, none of resource R2, and three instances of R3 it is requesting. Now if request J for that particular process I is equal to K, that means process Pi wants K instances of resource type Rj, like we explained over here. Now first of all we have to check whether this request is less than the need of that particular process. If the request is more than the need, that means the process is trying to exceed whatever it had claimed earlier. So it had given some maximum claim, and now if its request is more than its need vector, that means now this process is trying to exceed its maximum claim and an error has to be raised. Else if request is less than need, then we come to step 2. Now we check whether this request that has been raised by the process, is it less than the available vector? So whatever is the available resources in the system, the request has to be less than the available resources, then only it can be fulfilled. So if request is less than available, then we will come to step 3. Otherwise the process has to wait till resources are available. So currently these resources are not available. Now if request is less than available, then we will pretend that we have allocated the requested resources to that process, and we will say that available is equal to available minus request, because now these resources have been allocated to the process. And now after that we will assume that the process has completed its execution, and now when it will release its resources, then it will be considered as completed. But right now we are assuming that the resources have been allocated to that process, so they will be subtracted from the available vector. Also they will be added to the allocation matrix of the process, because now the requested resources have been allocated to that particular process. Also the need of that particular process will be subtracted by the request that was put in by the process. Now if we can find a safe sequence, then the resources will be allocated to that process Pi. Till now we were only pretending, but now if we have been able to find a safe sequence after this pretense is over, then these resources will be allocated to Pi. If we find that the system is in an unsafe state, then the process will wait and the old resource allocation state will be restored. So we will take an example to discuss this. So here we are assuming in this example that there are 5 processes P0 to P4, and there are 3 resource types A, B and C. A is having 10 instances, B is having 5 instances and C is having 7 instances. And this is the snapshot at time t0, the number of maximum that a process has declared. So P0 has declared that it will need a maximum of 7 instances of resource A, 5 of B and 3 of C during its course of execution. Currently it has been allocated 0 of A, 1 of B and 0 of C. So if we subtract allocation from max, then we get the need matrix. That means during its execution it might need 7 more, because you can see 7 minus 0 is 7, 5 minus 1 is 4 and 3 minus 0 is 3. So during its execution this process might need 7, 4 and 3 of the ABC resources. Currently how many are available in the system? When we add all of these allocated resources for A, we find that 3, 2 plus 3, 5 plus 2, 7. 7 instances of A are currently allocated. Total were 10. That means 3 are still available. If we add the B, So 1 plus 1, 2 instances have been used, total were 5. That means 3 are still available, and if we add the resource instances of C, 2 plus 1 plus 2, 5 have been allocated out of 7. So 2 are still available. So these are the data structures now we have at time t0. So now let's see whether we can find a safe sequence or not. So initialize work vector to be equal to the available vector, which is 332, and finish is initialized to false because all the processes are currently pending and no process is complete. Now we have to find an I such that false is the finish vector is having false and its need is less than the available. So we will start with I is equal to 0. So when we come over here for process P0, we see that its finish is false. So that is okay. That means this process is still pending execution. But if we compare its need with its available resources, we find that need is not less than available. Its need is more. So we come to the next index, which is index 1. Now if we compare this, we find that its need is less than the available because 1 is less than 3, 2 is also less than 3, and 2 is less than, so we have to find less than or equal to. So again 2 is less than or equal to C over here. So we have found an index 1. So this I is equal to 1. So we will assume that we have allocated its requirement, whatever it needed, 1 to 2, we allocated to process P1. So P1, it ran, it was executed, and now it is finished. So P1 has run now and it has completed its execution. So its finish will become, so this was 0, this finish will become 1, and now after execution it will release all its allocated resources. So now our available or the work vector will be updated and this 2 will be added to this over here. So this will become 5, 3 and 2. So the work vector has been updated. The finish vector has also been updated. Now we go to the next index. We go to I is equal to 2. We see is 600 less than the work, which is the available actually, whatever are the available resources. So we find that no, need is not less than available. So we go to the next index. Now I is equal to 3. So we are over here, finish is 0, its need is less than the available. So this is the next process to which we can allocate the resources and it can be run and executed. So we allocate resources to P3 and after P3 has completed, it will release the resources which were allocated to it, and so the available or the work vector will be updated. So now this will become 7 because now 5 plus 2, then 3 plus 1 is 4 and 2 plus 1 is 3. So now the updated work vector is 7, 4, 3 and finish vector will be also updated and P3 has completed. So this will also become 1 over here. Now what is the next index? Next index is 4. So is its need less than the available? Yes, it is less than the available. So now P4 can run, it will finish, it will release its resources. So the updated vector would be 7, 4, 5, 7, 4, 5 and its finish value will also be updated to 1. Now we go back over here and now we see what is the next. So we come to P0 and we see that now P0, the need is less than the available. So now P0 can be run. Now P0 will be updated by releasing its resources and its finish vector will become 1. So this new finish work vector would be 7, 5, 5 and P0 has done. And now when we check next, only P2 is remaining. So if we check 600 is less than 755, so now P2 can also be executed. So we have seen that we have found that safe sequence. So we have covered all the processes are being covered in this safe sequence. We have found that sequence, that this is the sequence in which the resources can be allocated to a particular process. So the system is currently in a safe state. Now let us see, suppose if a process P1 requests, this is the request vector now, 102, and this process P1 has put in this request. So first of all we have to check whether the request is less than the need. So P1, the need was 122 and it is requesting for 102. That means the request is less than the need. It is not exceeding its maximum claim. Now we will check whether request is less than available or not. So 102 is less than 332. That means these resources can be given to P1, but we have to check. Now this is the main underlying criteria of the deadlock avoidance. We have to check whether this allocation is going to leave the system in a safe state or not. So we assume or we pretend that we are giving this 102 to P1. So if we give 102 to P1, currently it was having 200. Now we have given it to P1. So now this allocation has become 302. So available will be subtracted by this request. So this will become 230 and need will also be subtracted by the request. So it will become 020. Now my work is 230. My finish is initialized to false. Now I have to find that safe sequence again, whether the system will be in a safe state or not if these resources are allocated. So if I go through the safety algorithm again, I find that this particular sequence will leave the system in a safe state. That means we have a sequence that will leave the system satisfied and all processes can be given resources if this request of P1 is considered. Since we have found this safe sequence, that means we can consider and grant this request of P1. So these resources that P1 had requested will be given or allocated to P1. Now let us say if P4 requests for resources 330. So if P4 requests for 330 over here, we see that it is less than its need. That means it is not exceeding its maximum claim. So if we allocate 330 over here, so this allocation would become 3, 3 and 2. Its need would be subtracted by the request, which would be 1, 0 and 1, and the available, now if you see, available is, the request is more than the available. So this is greater than 230. So as it is, this request cannot be considered because it is more than the available. So you will see that this cannot be considered. However, suppose P4 had requested for 230, then this would become 2, 3 and 2. This would become 2, 0 and 1, and this available vector would be 2, 0, 0, 0, because we would subtract the request from the available. Now can we find any such I over here which is for which the need is less than the available? No, there is no such vector, that no such I that we can find. So this request of P4 also 230 also cannot be granted. We will not be able to find a safe sequence. So in such a case, wherever the system is not able to find a safe sequence or the request is more than the available, those requests are not granted. So this is the basics of Banker's algorithm.